Hi guys, today we'll be talking about the PPO algorithm. So PPO algorithm is commonly used in reinforcement learning, which is a type of optimization problem, and it's used in many modern LLMs today. So which is why we're going to talk about it. So what will we be discussing today? First, we'll be talking about policy gradients. And then after that, we'll talk about the PPO algorithm itself. Afterwards, we'll talk about importance sampling. And finally, the clipping, which is one of the key contributions of PPO. So what exactly is the policy? So the policy decides what actions we take given a particular state. And we want to train this policy, right? So the way that we can do this is through stochastic gradient ascent. And so therefore we need the policy gradient. So you can think of the gradient as some expectation of the policy gradient. So okay, with some mathematical trick, typically is represented as the log. So log multiplied by the advantage. Yeah, and it is quite expensive to calculate the full expectation, so typically we just take the Monte Carlo estimate. So you just treat E hat as the Monte Carlo estimate, and this will give us a good estimate of the policy gradient itself. So the PPO algorithm makes use of this idea of the policy gradients. However, there's two loops, so let's explain the PPO algorithm. So the PPO algorithm, so we have two loops. So one is for however many iterations, big I, so however many iterations, then we will sample different trajectories. So for n is the number of trajectories, we will sample trajectories tau from the O policy, theta O, and then we compute the advantages of the different trajectories. So we compute the advantages, and now we optimize theta for t steps using SGD with the above policy gradient, and then we update with theta. So the reason why we do this is that it is usually quite expensive to sample different trajectories, and therefore in order to make it a little bit more efficient, we optimize this for t steps. However, this could be quite expensive. No, however, here we see that the trajectories which was sampled from the original policy no longer matches the current policy when we're doing stochastic gradient descent over multiple epochs. So how do we tackle this? So here we care about the expectation of the policy gradient, and one of the ways that we can estimate the expectation under a current distribution when samples were drawn from another distribution is based on importance sampling. So importance sampling allows us to estimate the expectation of a distribution when samples are drawn from another distribution. Okay, so let's go through the importance sampling. So suppose we have some new distribution which we want to find out. So what is this? So assume some discrete. So this is something like the sum of px fx, and now suppose we have some other distribution q, so we can arbitrarily do some algebra. So for example like this, and then if we shift the terms around, we'll get something like this. Sum qx px over qx. And if we look at this, this is exactly the expectation of q of this. Right, so now we do want to take the policy gradient based on the O trajectories, but using the most latest parameters which are updated with our stochastic gradient descent. So let's go through that. So let's say the policy gradient is this, right? Log pi but currently these trajectories are sampled based on we want based on the new policy, but the trajectories are sampled based on the old one. So now we have to add the importance sampling term. So this would be pi new s over pi o. Okay, so this is the importance sampling term, right? So this is the new policy gradient. So how does it, so what loss function is the PPO algorithm optimizing for, right? So we can find this out through some mathematical tricks. So let me get rid of this. Yep, so now we want to get the loss function, right? So this policy gradient is just a derivative of the loss function. So now what we can see is that, okay, so first I'll show the results and then we show how we derive it. So the loss is actually just the expectation of this new A given S policy of the O times the advantage. So this is, and then we'll call this R. Okay, so how do we derive this? So now let's assume we take the derivative of R, right? So what's the derivative of R with respect to the new theta, right? So what we have is O gradient of pi nu, right? And so how does this translate to this equation? So how it translates is that we see that we can actually use the log trick. So let's say we have some log of a function, and then we were to take a derivative of it, right? So by chain rule, so let's say we have some d over dx fx gx, sorry, fx gx, then this is equals to f prime gx g prime x. So in this case we will get f prime gx, which is 1 over fx f prime x, right? So in this case, if we treat this as log of the new policy, so if we take fx to be equal to the new policy, then what we actually get is the gradient of log is equal to the gradient of the policy over the original policy. Right, and now we bring this term over. So what we get is this term is equals to this new S and times the delta of the log. Yep. So now if we sub this into here, what we get is exactly this. Okay, so So now we have shown how this is the new loss function for the PPO algorithm. So finally, PPO just adds a clipping term on this R. So min R comma clip 1 minus epsilon 1 plus epsilon times A. So we want to have too large of a policy gradient update, and so the PPO algorithm adds a clipping term to it, to this R term. Yeah, and that's the PPO algorithm. Thanks for listening.